Imagine you are pushing a heavy truck or a bus across the floor. Have you ever thought about how much work you put into moving this object? And so today we will explore how to calculate such efforts, which we call work in physics. Today we will briefly discuss work in physics. That is what work is, how to calculate work, and also its applications in real-life scenarios. Before then, let me briefly introduce the broader context of work, energy, and power. Physics explores how objects interact and move. Work, energy, and power are interconnected concepts that helps us understand how force causes an object to move. That is, force causes motion and energy transfer. Work happens when a force is applied to an object and the object moves in the direction of the force. Work is the process of transferring energy to or from an object. Therefore, work is said to be done if only a force applied to an object causes the object to move. That is, there must be motion. The object has to change its position from its state of rest to another position. In that case, we consider work to be done. However, if an individual pushes a wall, the wall does not move, and so no work is done because we defined work as a force applied to an object over a distance. So if there is no displacement, that is, if an object does not move from one point to another, work is not done. The unit of work is the joules or the kilojoules or the Newton meter, depending on the context. Energy is expended when work is done because it takes energy to maintain a force when that force acts through a distance. Therefore, energy is the ability to do work, and it exists in different forms like the kinetic energy, also called motion energy. We have potential energy, sometimes called position or energy at rest, and the thermal energy, which we also call the heat energy. Work and energy are closely related since work transfers energy. Therefore, energy has same unit as work. Now let's talk about power. Power is the rate at which work is done. That is, it measures how quickly work is done or energy is transferred. Power answers the question of how fast can a task be completed, and the unit of power is the watt or the kilowatt. Having seen what work is, we did say that work is said to be done when a force moves an object a distance in the direction of the force. Therefore, formula for work is force multiplied by the distance moved by an object, or force times displacement times cos theta, where W is the work done, the unit is in joules, where F here is the force in the Newton, D here is the displacement, and the unit is in meters. Theta is the angle between the force and the displacement vectors. Now let me break down the formula and explain each term. Force in this context is push or pull. Displacement D is the distance moved in the direction of the force. We could see the force here. Of course, the movement is in the direction of the force. Theta here introduces the importance of direction. For example, if the force is perpendicular, no work is done. That is, we have our force here. If the movement happens to be in the opposite direction, then no work is said to be done, because for work to be done, the movement has to be in the direction of the force. Now we have a broader idea of what work is. Now we'll proceed to how to calculate work. Now let's look at the first challenge. A person pushes a bus across a frictionless floor for a distance 5 meters with a force of 20 Newton. Determine how much work is done on the bus. Now let's itemize the given parameters. We did say work done is the product of force. We could see that the force given is 20 Newton, and then given distance of 5 meters. And remember, we did say work done is the product of force times distance. So the work done is equal to 20 Newton being the force multiplied by the distance being 5 meters. So 20 Newton multiplied by 5 meters gives 100 Newton meter, which is equivalent to 100 joules. Now let's look at the second challenge. In the case of a 30 minutes working session, you lift a total of 12,000 kg, an average of 60 centimeters. How much work did you do? Now let's list out the given parameters. 12,000 kg means mass, 60 centimeters, that is the distance. But remember the SI unit of distance is in meters. Here we have centimeters. This simply means we are expected to convert 60 centimeters to meters by simply dividing by 100. So 60 divided by 100 gives 0.6 meters. And the challenge says you lift a total load of 12,000 kg. This simply entails that this work is done under gravity G. But work done in lifting the load is the product of force, where force is mass times acceleration. But because we are considering the work done in lifting this load of 12,000 kg, so we'll consider the work done under the influence of gravity. So the force becomes mass times acceleration due to gravity. So force equals mass, and the value of mass is 12,000 kg times acceleration due to gravity, which is 9.8 meter per second square. 12,000 times 9.8 gives 117,600 Newton. Remember, we said the unit of force is in the Newton. Now let's substitute these values into the work formula. So work is equal to the product of force multiplied by distance, and this gives 7560 joules. We can convert this value to kilojoules by dividing this by 1000. So 7560 divided by 1000 gives 70.56 kilojoules. So the total work done during the working session is 7560 joules, or 70.56 kilojoules. At this point, if you are getting value from this video and yet to subscribe to my channel, please kindly hit the subscribe button and turn on the notification bell. Thank you. Now let's look at the third challenge. A man pulls a sled with a rope at an angle of 30 degrees to the horizontal. If the force is 50 Newton and the sled moves 10 meters, find the work done. Now let's itemize the parameters given in the challenge. We are given angle, which represents the theta, 30 degrees. We are also given force, which is 50 Newton. We are also told that the sled moves 10 meters, which means the distance. These two formulas represent the formula for work. In our question, we are given angle, theta, so the second formula has theta. We are given force, which the second formula also have, and D being the distance. So the most suitable formula to apply here is this one. That is work done equal force times distance times cos theta. The value of force is 50 times distance, which is 10, times cos theta. Our theta value is 30 degrees. 50 times 10 gives 500 times cos 30 degrees, root 3 over 2. And so 500 times root 3 over 2 is approximately 433 joules. And so the work then is 433 joules. Now let's move to a more complex challenge. Mercy is at an amusement park and pushes her 25 kg little brother horizontally on a swing hanging by a 15-meter cable. How much work must Mercy perform to slowly push the swing away by 1 meter from the vertical? Additionally, how much work does gravity do on the swing during this displacement? We could say this is a more complex challenge. First, we'll have to itemize all the parameters given. Let's even try to understand the geometry of this challenge. Here we have 25 kg being the mass of the little boy, while H1 represents the length of the cable being 15 meters. H2 represents the horizontal displacement moved by the swing after Mercy slowly pushed the swing. Here we have horizontal displacement. Now we are expected to calculate the vertical displacement. The vertical displacement will be equal to the square root of 15 square being the length of the cable minus 1 square horizontal displacement. The square of 15 is 225 minus the square of 1, which is 1. So 225 minus 1 gives 224. The square root of 224 is approximately 14.97. So the vertical displacement is 14.97 meters. Let's not forget to include acceleration due to gravity G, which the value is 9.8 meters per second square. Now let's calculate change in height. Let's represent change in height with this is equal to 15 meters being the length of the cable minus the vertical displacement, which is 14. So 15 minus 14. gives 0.03 meters. Now let's calculate how much work gravity will do on the swing during this displacement. The work done by gravity is related to the change in gravitational potential energy. That is negative mg change in h equal to minus m stands for the mass of the little boy being 25 multiplied by g, our g value is 9.8 multiplied by change in h, that is 0.03. So we have negative here. 25 times 9.8 times 0.03 gives 7.35. Therefore, the work done by gravity is negative 7.35 joules. Now, let's also find the work done by Messi in pushing this swing. To push the swing slowly, Messi does work against gravity. That is, the work done is equal in magnitude, but opposite in side to the work done by gravity. Therefore, the work done by Messi is 7.35 joules. I hope this video is clear enough. Please, if you really got value, give this video a thumbs up. And if you are yet to subscribe to my channel, kindly hit the subscribe button and turn on the notification bell. Also, do well to share this video with anyone who might find it useful. Comment with any question or topic you would want us to cover in future video. Please be on the lookout for the next video where we'll solve some numerical problems on energy and power. Thanks so much for watching. See you in our next video. Bye.